Okay, so to actually now evaluate the integral over the surface of the box, first thing that we should try to do is let's write down these area elements dA on each of the various sides. So let's start off with the right side here. So we've got dA. Now take a look. For dA, we said the points y and z can be anything. So y and z are the two coordinates on the surface of the box. So the size of some little area element is going to be dy dz. And then in which direction does dA point? Well, if you look at the right side in this figure, if it's pointing outside of the box, it's pointing in the x hat direction, the unit vector that points in the positive x direction. So now let's take a look at the left side. So we've got dA will be equal to, again, it's y and z that can vary. But now our unit vector on the left side for dA, it has to point outside of the box, which means along the negative x direction. So we'll have a minus x hat. I hope that's clear. Okay, why don't you try to write down the area element for the top side? So pause the video, do it, and then we'll continue together. So pause now. Okay, good. Do you have an answer? So for the top side, x and y can vary. So we'll have dx, dy. And for the top side, we're pointing along the positive z direction. So along the z hat direction. For the bottom side, you could try this again. So you could pause the video and try it. So what's the answer? Again, we're integrating over x and y. So we'll have a dx, dy. And now for the bottom of the box, we must point along the negative z direction, so minus z hat direction. For the front side of the box, well, the coordinates that are varying are x and z, so we'll have a dx, dz, and the front side of the box, well, that's pointing along the y hat direction. There's one more area element left, and that's for the back side of the box. And again, the coordinates that can vary are x and z, and dA will point in the negative y direction. So there are the 6 area elements for this integral. And then the only other thing that I should specify are what are the components of this field, this vector field f. Well, it'll have an x component along the x hat direction. It'll have a y component along the y hat direction, and a z component along the z hat direction. So I can now plug everything in. So this will be equal to. So let's now take a look over the right side. So if we're integrating over the right side, we'll have an integral over dy, an integral over dz. Both of these integrals will go from minus L up to L. When we take dA dotted into f, well, the x hat from dA dots into the x hat from the f to give us fx. And we get 0 with dotting into y hat and dotting into z hat. So that's the only contribution. Fx is evaluated at x is equal to L and any value of y and z. Good. Okay. So I wrote down the contribution coming from the right side. Why don't you try to write down the contribution coming from the left side, and let's see if we get the same answer. Okay, pause the video and try it. Okay, you got an answer. Good. This is what I got by doing exactly the same thing. So again, an integral dy, dz, minus L up to L up to L. The reason why there's a minus is that there's a minus sitting inside dA for the left-hand side. And then we've got fx. We have got x at minus L, and then y and z. Okay. Next, let's write down the contribution from the top side. So pause the video and do it. This is my answer. F. Now, for the top side, we're proportional to z hat. So we'll pick up the z component of the vector field. It's any x, any y, but z is all L because we're integrating over the top side. And then when we integrate over the bottom side of the box, again, dA has got a minus in it. So we'll have a minus integral dx, dy, minus L up to L. Then we will have fz at any x, any y, but now it will be at z is equal to minus L. Then let's go over the front side. So you could pause and do it unless you're bored out of your skull, in which case you can just watch me do it. Maybe I'll make a mistake. That'll make it interesting. So we've got an integral dx, an integral from minus L to L dz. So on the front side, it's x and z that vary. The area element has got a y hat in it, so we're picking up the y component of the field. Any x, y is equal to L, and any z. And then minus, and now we will have an integral for the backside of the box. Z, fy, any x, now y is equal to minus L, and any z. Good. Okay, so that is exactly what our integral looks like after we've used the divergence theorem. Now, what you will notice is this is entirely an integral over the surface of the box. Top, bottom, left, right, front, back. So whatever this field F is, maybe it is a current of some type, an electric current. It could be an electric field. It could be a momentum current. But whatever this vector is, it will tend towards zero. Why? We really imagine that the box that we're in is infinitely big, and whatever we've got placed inside this box is deep in the middle of the box, so that by the time you get to the edges of the box, the surface of the universe, all fields have dropped to zero. So this is equal to zero, and the reason is since F vanishes on the 6 sides of the box on dV, okay? So that's again the reasoning. And you can see that this integral of a total derivative has landed up giving us the integral over something that lives on the surface of the universe, on the surface of the box, where all fields vanish. Great. So now let's move on to the 4-dimensional version. That's actually the version that we need for the Euler-Lagrange equations.